Hell yeah. Thank you. Oh yeah, and take a photo of that if you want to keep that info.
I'm going to put this on LMS later today as well.
Okay, thank you.
Just don't forget to snap a photo of it and send it to me, okay? Oh, sorry. All right, next door, can you hear me? Thank you. Okay. All right, so in the first lecture, we basically reviewed how we find local extrema functions of a single variable, and I highlighted some common mistakes that are made, particularly the fact when sometimes the second derivative test fails, and in those cases if you are using the second derivative test, you'd be expected to revert to the first derivative test, and the common mistake about saying if the second derivative is 0, it's automatically an inflection point. Not necessarily true. So inflection point's one where the second derivative must change sign as well. Again, the easiest way to remember it is think of the function y equals x to the 4. We know what it looks like. We know it has a minimum. So the fact that the first and second derivative are both 0 at the origin, it's clearly not an inflection point. All right? Now we're going to go through how we do something similar, but now with functions of several variables. And as I hinted at last week, the way we do this is with the gradient vector. All right? So most of the ideas can be logically extended to functions of 2 or more variables. We'll stick to 2 variables because, again, that's what we're familiar with visualising. So basically the idea of a local maximum and a local minimum is the same idea as a function of a single variable. By local we mean suitably close. All right, so when we were doing it with, say, functions of a single, like this one, for example, this is a local maximum. By local, I mean not too far away from it's a hump, right? But not too far away, I don't care what it's doing. So local maximum, local minimum. The same idea extends to functions of several variables. But the catch is now, how do we find them? So a function of a single variable, right, remembering that the derivative gives us the slope of a tangent line, it makes sense to look for places where the tangent line is 0. The analogue in function of two variables is the tangent plane. So we look for where its derivatives are 0. Right? And that's actually what the gradient vector is telling us. Remember, the gradient vector is a vector made up of the partial derivatives. Right? So again, but local maximum if it's got a hump, a local minimum if it's like a trough or a valley. Right? Now, how do we find it? Well, you imagine if you're sitting at a local maximum, there is no direction of greatest increase, is there? Right? Because you're at the top, right? Which means there's also no direction of greatest decrease. So if you had like a small enough ball bearing or something, if you're right at the top, it should balance there. There's nowhere, it won't roll anywhere, right? That's basically what we're saying. Same at a local minimum. There's no direction of greatest decrease. Hence, there's also no direction of greatest increase because they're opposites of each other. So to find these points, what we do is we find the gradient vector and we set it equal to the 0 vector. That's another way of saying, remember, what the gradient vector tells us is the direction of greatest increase, or turning it around 180 degrees is the direction of greatest decrease. If there isn't one, that's the same as saying the gradient vector is 0. It's another way of saying there is no vector. So the 0 vector is just the origin, right? In other words, it's saying there is... There is no... Oh, God, awesome. What was I saying? Right, that there is no direction, right? So basically we set the gradient vector equal to 0. So for a function of two variables, we're going to have two equations in two unknowns, partial df dx and partial df dy. And we solve them. Here is the catch. Those equations will not be nice, simple linear equations like you used to. Right? So with, remember when you've got to solve two linear equations in two unknowns, we teach two methods. There's a substitution method or the elimination method, right? So the reason we teach both is because when we have nonlinear equations, we might need both, right? So the hardest part of solving these problems is figuring out what is the best way to attack solving these two equations into unknowns. I mean, that's the big difference between linear mathematics, which is simple but boring, and non-linear mathematics, which is not simple but extremely interesting, right? And that's the hardest part. It's a skill that comes with practice. The best advice I can give you is when you're solving these problems, you find the two first-order partial derivatives. You've got two equations in two unknowns, but they won't be linear equations, right? And then put your pen down and look at them. Right? And you need to think about what is the best way to solve. I can't give you any hard and fast rules, use this method, use that method. When things are non-linear, we don't know. Right? So you write them down, then you look at them and decide what's the best way to go. And again, it's a skill that will come with practice. You do enough examples, you'll get like a bag of tricks, essentially. Not tricks isn't the right word, but a bag of techniques on how to solve them. Right? Right, so basically, we have a similar definition of critical point. So a critical point is where the gradient vector equals 0, the 0 vector, or the gradient vector is undefined. We're probably never going to do ones where the gradient vector blows up, because those surfaces will be very strange. So most of the time it's the first one, right? That where you're looking for points where the gradient vector just equals 0. Let's have a look at an example, right? A very simple one. Let's look at these three surfaces. Right? Z is x squared plus y squared, z is 1 minus x squared plus 1 minus x squared minus y squared, and z equals y squared minus x squared. If I find the gradient vector of all of those three, first one I do partial df dx, partial df dy, that's just 2x and 2y. Second one you get minus 2x and minus 2y, and the third one you get minus 2x and plus 2y. You want this equal to the 0 vector, two equations in two unknowns. These ones are easy. In other words, we need, for all three, we need x equals 0 and y equals 0. The key is the pairs of points you find must satisfy both components of the derivative. Satisfies one and not the other, it's not a critical point, right? They've got to satisfy both. And of course, we know what these surfaces look like. The first one's basically like a paraboloid, like a parabolic cup or something like that, and obviously it has a minimum at the origin. The second one's cup upside down, it obviously has a local maximum. The third one, however, looks like this, and that's neither a max nor a min, is it? Right? We call these saddle points, right? So the critical points for a function of several variables either is a local max, a local min, or a saddle point, right? But note that there's no first derivative test for a function of several variables, right? Because to prove, say, that this is a local maximum, I would have to prove that the function is decreasing in any possible direction from that point, and I can't check them all, right? So unlike functions of a single variable where we have a first derivative test and a second derivative test, for functions of two variables, we only have a second derivative test, which we'll go through in the last lecture. Right, so this lecture, all we're going to do is locate them. We're not going to bother classifying them at this stage. But they'll be local maximums, local mins, or saddle points. There's only three. Okay? Right. Now, there's also an analogue of the extreme value theorem, right? But this will be, as we'll discover, will be a lot more work. Right? So this definition of a boundary, basically, think about the extreme value theorem for a function of a single variable. So if we go back here, we say that we've got this interval x is between a and b, and it includes a and b. It's got to be a closed interval, right? So hence I use the square brackets. All this definition stuff here, right, is basically saying open, closed, and bounded. Basically, when I ask you to do an extreme value theorem, it will be closed and bounded. Right? But closed means the actual boundary is always included, because when they're not, those are very hard problems. Right? So that's all that's basically saying. Best illustrated with an example. Right? So the extreme value theorem, basically similar to a function of a single variable. The absolute maximum and absolute minimum for a surface, provided it's smooth and perfectly well behaved, it doesn't blow up, doesn't have any holes in it, that sort of thing, will either occur at critical points or along the boundary. Right? But now think of this carefully. For a function of a single variable, the boundaries are just constants. Right? If you've got to optimise something, say x between a and b, you find the value of the function at a, you find the value of the function at b, and off you go. All right, obviously this is going to be stuffing up the recording and next door. Next door, bear with me, I'm going to reboot the system. Talk amongst yourselves. Right, because this will be stuffing up the recording. So let me just, classic thing, turn it off and on again. All right, just give me a sec. right, next door, can you hear me and see me? Great. Right. So, extreme value theorem, a similar idea, but instead of just checking 2 points, you've got to check the whole boundary, and sometimes the boundaries can be a lot of work to check. Again, this is best shown by an example, but the key is the ideas are the same. Just like with everything with functions of several variables, there's a bit more algebra to do, and actually the hardest part can be, depending on the function, can be finding the critical points in the first place. So the key is that when you've got to solve these two equations into unknowns, write them down, and then, unless they're very straightforward, look at them, and you've got to decide what's the best way to attack them. And like with most things, it's a skill that will come with practice. Okay? All right, let's have a look at an example. So I want to do this. Let's first imagine all this question asked was locate the critical points of this surface. All right, let's just say that's all it said. All right, so we've got basically z is 2x squared plus x plus y squared minus 2. So what you do is technically what you're doing is you construct the gradient vector and set it equal to 0. In other words, you find partial df dx, partial df dy, set them both equal to 0, very similar to what you do with a function of a single variable. You find the first derivative, set it equal to 0, solve for x. Here you find the first partial derivatives, set them both equal to 0, solve for x and y. Two equations in two unknowns. Right? Now, of course, partial df dx, that's just 4x plus 1, and partial df dy is 2y. Linear, easy. Right? So I can solve them, they're what we call decoupled or uncoupled. One only involves x, one only involves y. Life is good, this hardly ever happens. All right? But you can solve this straight away. The first one's basically, remember, you've got to find pairs, x and y. You're looking for coordinates, x and y, that satisfy both. Now, the first one is basically saying x equals minus a quarter, y can be anything. Yeah? The second one is saying y can be 0, x can be anything. But you need a pair that satisfies both. Right? So there's only one pair. X is minus a quarter, y is 0. That satisfies both simultaneously. So there's only one critical point. Right? Now, going back, now let's say I want to find the maximum, absolute maximum, and absolute minimum of this function on this closed region. So for all x squared plus y squared less than or equal to 4. So in the xy plane, that's a circle. What that black line is the projection of that circle onto the surface. Right? Now, because we're drawing this on 2D, and this is a 3D problem, unlike a function of a single variable, you can't tell by looking at it what's highest and what's lowest, can you? Right? Now, obviously, lowest you probably could, right? It's obviously going to be the hump down the bottom, right? But somewhere on that curve is the highest, and we have to find it, right? Now, when we do function of a single variable, you just chuck in the value of the endpoints and compare. We do the same thing here. We chuck in the expression for... Did that just switch off again? We chuck in the... You piece of... We chuck in the expression for the boundary. Oh, no, I can't. Let's try this. Next door, can you still see everything? Yes. Thank you. Right, let's try this. Come on, you've got to last like 20 more minutes. Right. We chuck in the expression for the boundary, then it becomes a function of a single variable problem. Yeah? So the boundary is x squared plus y squared is greater than 4. Right? Now the function I'm trying to optimise is 2x squared plus x plus y squared minus 2. So somehow I've got to combine these two. What I'm looking for is an expression that tells me how the function's varying just on this black curve. right? So I could use, I'd like to avoid, if I can, bringing in square roots. So the fact that the surface has equation 2x squared plus x plus y squared minus 2, the smartest way would be just to eliminate y squared using this, wouldn't it? Right? If I use this to eliminate x, I've got two problems. Right? X is plus or minus the square root of 4 minus y squared, and things are nasty. Right? I'm not going to give you ones like those. Right? So it's simpler to eliminate y squared, and that'll give me a function of a single variable that I already know how to optimise. And this becomes a extreme value problem for a function of a single variable, because I'm only interested in x between minus 2 and 2, because I'm constrained x squared plus y squared equals 4 is a circle of radius 2, so x goes between minus 2 and 2 and y goes between minus 2 and 2. Right? So I've got to find the extreme values of this one. I know how to do that with a function of a single variable. So the only critical point is x equals minus a half. Right, so I've got the endpoints, I've checked all the endpoints, and then I just compare everything. So it's a similar idea to function of a single variable, there's just a lot more work involved. So the extreme value questions for functions of several variables will be a lot of work depending on the region. I'm going to go through another example in a sec. Right? But the key is that what you're doing is a logical extension of what you do as a function of a single variable. Just like with differentiation and stuff though, it's a lot more work, and the two equations in two unknowns will hardly ever be linear. They could be anything, and you have to use logic and have to think about what's the best way to solve them. Right? Now let's illustrate this by looking at some examples. There's one in particular I want to All right, let's have a look at this first one, then I'm going to do another one by hand. Let's say I asked you to find the critical points of this surface. All right? So all I do is I find the two first order partial derivatives and I set them equal to 0, so I've got two equations in two unknowns. All right? The thing to remember is you've got to satisfy both. Right? You need pairs of points, not single points. You need pairs of points that satisfy both. Now if I find partial dz dx and partial dz dy, right, I get minus 2x. When that equals 0, that's saying x equals 0, y can be anything. Right? When I solve the second one, I only get y. So this is another one where we say they're decoupled. In other words, one only involves x, one only involves y. They're the good ones. Hardly ever happens, unfortunately. Right? Now, if I solve the second one, same deal with function of a single variable. The only thing I expect, quadratics, I'm not going to give you anything terribly, I'm not going to give you like an order 7 polynomial and expecting you to know how to solve that sort of thing. Although this looks like a cubic, it has a common factor of y, so it's y times a quadratic. Right, but here's the thing, right? So there are three critical points. Right, because all three of these pairs, x equals 0, y equals minus 3, x equals 0, y equals 0, and x equals 0, y equals 4, satisfy both pairs of equations. So there are three pairs of critical points. Right? You've got to think about what this is saying. This is saying partial dz dy, y can equal these three, and x can be anything. But the constraint of the first one tells me x has got to be 0. Yeah? Right, so there are three pairs. Right. This one I want to do by hand. All right, so the second one's asking, hang on, whoops. Sorry, next door, hang on a sec. I hit the wrong thing. Right. Now the second question is find the critical points of the surface Right, so the problem with this one is the partial derivatives aren't going to be linear, and they won't be decoupled either. If you think about it, if you initially look at them. So the first thing to do is find the partial derivative. So this one I need to use the product rule. So second bit times the derivative of the first bit plus the first bit, so remember the order I do the product rule in, times the second bit. Right, clean it up because I'm going to have to solve this damn thing. Right, so if I right, now I factored this one because I know I'm going to have to solve it next. Right? And if I do the same partial dz dy, that one's actually relatively straightforward. Right? These ones are coupled, which means x and y appear in both. Right? But the next step is, of course, you then set both of these equal to 0 and you solve them. Right? And this is where you've got to look at them and think about what's the best way to go. Right? Now, of course, the first thing to notice is they both have e to the x in them. E to the x never equals 0. It gets close to 0 as x approaches minus infinity, but it never gets there. So it is safe to assume, you know, that when you've got a times b equals 0, either a equals 0 or b equals 0 or both a and b equals 0. That's true of linear, non-linear, whatever. Right? So that second one's basically, if I look at the second one, that's saying either y equals 0 or e to the x equals 0. E to the x never equals 0. So the only possible solution of this one, y is 0, x can be anything, will satisfy the second one. Right? That means, well, that means if y is constrained to be 0, then what the first one's telling me is that either e to the x equals 0, it can't, or the only possibility x squared plus 2x plus 2y squared has to equal 0. But I now know that y is constrained to be 0. So the first one's actually telling me that's the only possibility. Right? Because I solved the second one first. Right? And I can't give you any hard and fast rules which one you attack for. It depends on the question. Now, because this is easy to solve, and remember, I'm always going to give you things you can solve. If you end up with something, you're not doing it right. Right? Or I've stuffed up, one or the other. If I factor this out, right, so this one's got 2 pairs of points. So therefore, right, and as a quick check, you can make sure that they satisfy both partial derivative equations. Right? But you've got to look at them and think, what's the best way to attack this? Right? That's the key thing. I don't want to do that one just yet. Where is... Right, here's one that we're going to look at tomorrow, but I just want to illustrate something. You don't have to write... This is in example set 3. Right, I'll just frickin' show you. No point hiding the bloody thing. Right, in example set 3, which we're not ready to solve yet, locate and classify... Let's imagine all it says for now is locate the critical points of this one. I want to illustrate something with this one. Right, so let's say we've got to just locate. Can't classify yet because I haven't shown you how. All right, we've got to locate the critical points of this surface. All right, same deal. Find these partial derivatives first. All right, and you set them both equal to 0. Which is the easiest one to start with? The second one, isn't it? Right, because you can do it. Can't solve the first one yet. Notice they're coupled. Right, and coupled is bad. Right? You have to find some way to decouple them. What's the second one saying? Here you've got to use logic. You've got to think about what you're doing. The second one is saying either x equals 0, y is anything, or x is anything, y is 0, or they're both 0. That's what that simple equation is saying, those three possible cases, aren't they? Right? Right, so the second one's telling me, this one implies just x equals 0, or just y equals 0, or they're both 0. Right? I've got to make sure I make sure everything's working. Now I go back to the first one, right? Because I've got two equations in two unknowns. Now when x equals 0, the first partial derivative tells me that, well, I've got... life is good. So I have two pairs already. 0, 1 and 0, minus 1 is a suitable pair, a valid pair. Yeah? If y is 0, then the first one's telling me so I've got two more pairs, 1, 0 and minus 1, 0. Now what about the case, that certainly satisfies the second equation, doesn't it? But now the first equation tells me, which is obviously bullcrap, right? So this is not this is not a valid solution. It satisfies one, but not both. So 0, 0 is not a critical point. Yes?
Surely you've tested that case in the processes.
Depending on the question, there won't be you have tested that case in this one, but depending on the question, you do have to be careful, right? Because if I ask you then to classify them, you don't want to be classifying points that aren't actually critical points. It's a waste of time, right? So you've got to be clear that you found them all, right? So in this case, this has got, right? But you have to be careful, right? That's the point I'm trying to make, right? So this one has 4 pairs. So therefore, the critical points with what have we got? We had minus 1, 0. Of course, the order you write them in, I really don't care. Right, so but this one's got 4 pairs of critical points. The other one, 0, 0, is not a critical point. It satisfies one, but not the other. All points must satisfy both. And as a quick check, what you could do is you could plug those 4 points into both, make sure they work. Okay? All right, let's have a look at one more. Let's have a look at this one. This is also from example set 3, which is locate and classify. But let's just say for the moment it says locate. Let's say we've got to locate the critical points of this surface. All right, same thing. Now, how should we proceed? Also note that the technique, there might be several ways to do this. That's the beauty of nonlinear mathematics, right? There are no rules, right? Anything could happen. What's the first one saying? Basically, x squared equals y squared. It's not really helping me, is it? X equals plus or minus y, or y equals plus or minus x. Right? It's not telling me much, right? And of course, cases. Ooh. Let's see if we can avoid it. What's the second one telling me? If I look at the second one, what's that telling me? Well, if I play around with this one, right, so now what's the second one telling me? Either y equals 0 or x minus y squared equals 0. Or they're both 0. Right? So this one's implying or right. So we could either have y equals 0 and x equals y squared, or y equals 0. So either y equals 0 or x equals y squared, or x and y are both 0. Now notice, unlike the previous one, x and y both 0 matches the first one. So 0, 0 is a critical point of this one. Right? All right, now, this one's telling me that. I don't want to take square roots yet, see if I can avoid it so things don't split into cases. Right, now, if I look at this one, right, so when y equals 0, this one tells me x equals 0. So that's one pair of points. So 0, that case is done, and so is this one. Yeah? Now all I've got to worry about is this case. So I've basically got these two equations, that x squared equals y squared and x equals y squared. Right? So in other words, these two combine to give me that, don't they? Remember when we've, never divide, always factor, so that gives me those two solutions, right? Which also tells me that either y is 0 or y is 1. Right? And that's it, there are no more. Right? So this one only has, well, what have you got? You've got x equals y squared. So this one tells me that y's got to be 0. When x is 1, you either get y, you basically get y squared equals 1. So y can be plus or minus 1. Right? So then you put it all together. Right? So we've got 3 critical points. 0, 0, 0, 1, and 0 minus 1. And, 1, 1, and 1. 0, come on, brain. 0, 0, 1, 1, and 1 minus 1 are the 3 valid pairs. Yeah? Right? Again, this is the hardest, solving them is the hardest part, especially when they're non-linear. You have to be careful, make sure you don't get superfluous ones and that you pick up all possible solutions. And I say, I can't give you any sort of hard and fast rules because things are non-linear and anything can happen. Right? We're going to do some more examples tomorrow. The last thing I wanted to go through is, right, so where were we? All right, so we did that one. I did that one by hand. And this question 3, find the absolute maximum and the absolute minimum of that function on this rectangle. Right? So it's basically a rectangle in the xy plane. So the extreme value theorem tells me, well, if the surface is well behaved, these are all just powers of x. There's no dividing by 0. Nothing's blowing up. So everything's fine. The absolute maximum and absolute minimum will either happen at critical points or somewhere along this boundary. Now I can find the critical points first. Partial df dx, partial df dy. You get 2x minus 2y has to equal 0, and minus 2x plus 2 has to equal 0. Notice the second one tells you x can be 1, y can be anything. What does the first one imply? When x equals 1, that y equals 1 is the only possible pair of solutions. All right? So we've only got the one critical point. The only critical point is 1, 1, and the value of the function at that point when x equals 1 and y equals 1 is just 1. The next thing is, okay, now I have to figure out what the function is doing on this, this surface that sits above this boundary. Right? And because it's a rectangle, that's what the boundary looks like in the xy plane, right? Basically just a rectangle. X between 0 and 3, y between, 0 and 2. Right? What I do is I break it into 4 pieces. Right? And I've called them L1, L2, L3, L4. Right? You can call them whatever the hell you want. Right? Line 1, line 2, line 3, line 4. I've got to figure out what the function is doing on each of those boundaries. Now, along line 1, y is 0, x goes from 0 to 3, doesn't it? So the surface behaves like x squared, where x goes from 0 to 3. Right? And then that becomes an extreme value theorem problem for a function of a single variable. In other words, find me the absolute maximum and absolute minimum of x squared between x equals 0 and 3. I don't even need calculus for that. I know what x squared looks like. Between 0 and 3 it goes whoop. All right, so at 0 it's the minimum, 3 is the maximum. Done. Yeah? So the minimum is 0, the maximum is 9 along that part. Along L2, I've got x is 3, y goes from 0 to 2. Right? My surface looks like 9 minus 4y, basically plugging in x equals 3 and letting y vary. Function of a single variable. Straight line, I know what that does, right? So its maximum is when, because it's a straight line with a negative slope, maximum is at y 0, minimum is at y at the other end point, isn't it? I don't even need calculus for that one either. Along L3, what have I got? I've got y is 2, x goes from 0 to 3. Right? Now I get a parabola. A parabola, but I could use calculus to do it, but if I recognise that it's a parabola basically at x equals 2, right, and which is smack in the boundary. So the maximum will be its furthest left point and its minimum is its turning point. You could use calculus for that too. Right? Then along L4, I've got x equals 0, and I get a straight line. I don't need calculus to optimise that either. Right? Then I compare them all. So I've got the absolute value, the value of the function at the critical point, and I've got the maximum minimum the function can take along each boundary. Which is the biggest? So I've got a 1, a 0, a 9, a 9, a 1, a 4, a 0, a 4, the biggest is 9. And that occurs at when x equals 3, y equals 0, which is the same as this point, because that's where the two line segments meet, basically. And the minimum, I've got a 1, 0, 9, 1. I think the minimum would be 0. That's at the 0, 0 or 2, 2. And that 0, 0, that's already taken care of. Right? So it's a similar idea, function of a single variable, just a lot more work. Okay? All right, what I'd like you, in particular this question, what I would like, actually, obviously try and do all the examples, but do this one yourselves. right? This example 3 yourself, right? Because basically this brings it all together into one single problem, right? And then in the last lecture this week we'll talk about how we classify these points, right? But we'll leave it there for today. Sorry about the trouble with the projector. Remember, I have consultation tomorrow 9 till 12 if you need some one-on-one help for the test this week, all right? And I'll see everyone on Thursday. Did you email me that? Did you email